Alright, let's take a look at the real nasty looking non-perpendicular vector problems. What makes these ones so complicated is that both the vectors don't have that straight horizontal 0-degree direction. So look at this problem. This is from your review for the test. Find the magnitude and direction of a resultant of two forces of 125 pounds and 60 pounds at angles of 40 degrees and 165 degrees with the x-axis respectively. Pretty tricky to picture on paper, up there in your head, so let's try and put this on paper as best we can. Picture should look something like this. So if we have an x-axis, which you can see with the dashed line here, we have to have a vector at 125 pounds at a direction of 40 degrees. And then we have to have another vector of 60 pounds at an angle of 165 degrees. So we're still going to stick to the plan that we did for even the simpler non-perpendicular vectors. We still have to sketch the resultant tip to tail, so let's do that first. So now that we did tip to tail and sketch the resultant in there, notice that we can see r. And theta is tough to spot, but if we kind of unhighlight the rest of this stuff here and just focus solely on r, you can now see that the angle that theta is going to be here is this angle right there. There's theta. So you can see that that's going to be kind of a trickier problem to try and figure out how many degrees that is, because you have so many other angles going on inside that angle of theta. But the good news is once we figure out the plan, it's really pretty straightforward to know what we need to do to get it. So now finding r, we're going to have to go back to the triangle that we just made here. So now the key next step here needs to be setting up the law of cosines here. The only way we're going to be doing that, to do that, we need to figure out how many degrees this angle is right here. Why that angle? It's because it's opposite from r. So this could be kind of a task to figure out what it is. Now the key to figuring out what this is once again setting up parallel lines and finding alternate interior angles or corresponding angles. It's really tough to spot on these ones. You might go through a couple of different attempts before you actually nail down a quick way of getting it. But if we really look closely here, when we just focus on the two vectors again, and only the two vectors that we started with, that 165 degree vector along with that 40 degree vector, it's pretty straightforward on how to figure out how much angle, how many degrees are in between these two. Just a simple subtraction problem. We can take 165 degrees and subtract the 40 degrees. So now that we're looking at that 125 degree angle measurement there, take a look at this move that we're going to do next. If we extend this vector that we used with tip to tail here with a dashed line right here and extend this one here, we've created alternate interior angles, or even supplementary angles. If you guys remember same side interior, that'll help us nail down the degree measurement here, the one that we needed in the first place to figuring out r. So with same side interior angles, with this 125 degree measurement here, we can subtract 180 degrees from 125 and arrive at the angle that we're going to be using here for the rest of our work. And there we have it, 55 degrees. Now we're going to use that 55 degrees with r and use the law of cosine. So let's get that set up and let's bring back some of the information in the triangle now. So with this triangle, let's make some room for ourselves over here on the side and let's do the law of cosines. Let's set that up again. So we run right through the law of cosines there, and we kind of speed up this process here a little bit, and we arrive at our final answer there of 103.1 pounds. Now let's try and figure out what theta was. Now keeping the same triangle here, now it's time for step 3, which is the law of sines. Keeping the same triangle here, let's try and figure out how many degrees this angle right in here is. We can figure that part out. But realize that it was not the final angle for the direction. Remember, the final angle for our direction for the vector is this whole thing right here. But as you can see here, if we can game plan this out, if we can figure out the blue angle using the law of sines, we can find the green angle, which is our ultimate direction for the vector, by just simply adding the 40 degrees to it. So let's find that blue angle using the law of sines. Set up our proportion here, sine of 55 over the 103.1 that we just found up above, and set that up to the sine. I'll just call it alpha. I don't want to call it theta since usually I'm using theta as my final answer. and have the sine of alpha over 60. And I highlight in blue just to show you that I'm finding the blue angle right there. So cross multiply and divide, we get the 0.477. Inverse sine, don't forget about that part, I kind of left that part out of here. You have to take the inverse sine of 0.477 to get us to that angle right there. This is just that angle in blue right here. So now to figure out our final direction here, we're going to tack on that 40. So when we add our 40 degrees here, we get to our final answer for theta, which will be that 68.5 degrees. So we accomplished both our goals here. We found the magnitude and we found the direction of that new vector.